Welcome to my lecture. In today's lecture, we are going to solve a problem where we'll have a vectors from R2 and a matrix A, and then we have to show that the the identity given here x comma y equal y transpose multiply A multiply x is an inner product. So to show the inner product, we have to verify few properties. So first one is that x is defined as x transpose ax is non-negative. So x transpose, so this column vector will become row. So x1, x2, and then the matrix A, and then x is as a column vector. Then we take the multiplications of these two, and it will become 3x1 minus 2x2, and then minus 2x1 plus 4x2, and then this column vector x1, x2. Then we further multiply these two matrices, and then we will have 3x1 square minus 2x1 x2 minus 2x1 x2 plus 4x2 square. Then we will try to make it perfect square so that this expression will be non-negative. So from this 3x1 square, we take 2x1 square and arrange the remaining part like this. So this arrangement has a significance because this will gives us a perfect square, the underlined part. So what is that underlined part will reduce to? So this will become x1 minus 2x2 whole square. So clearly this is positive and equal to 0 when both x1 and x2 equal to 0. So therefore this is non-negative and xx is equal 0 if and only if x1 is equal 0 is equal x2, that means x is equal 0. So this verify the first property for the inner product. Now we have our second property, which is the symmetry, that xy is equal yx. The operation xy is equal yx. So xy is defined as y transpose ax. So y is this column vector. So y transpose will become row vector y1, y2, and then the matrix A, and then the matrix x, the column vector x. Then again, we will multiply this with the matrix, and we'll get 3y1 minus 2y2, and this is minus 2y1 plus 4y2, and then we'll have a column vector x1, x2. Then we further multiply this, so we'll get 3y1 x1 minus 2y2 x1, and then minus 2y1 x2 plus 4y2 x2. Similarly, we calculate yx, which is x transpose a y, and then x transpose is x1, x2, a is the matrix, y is y1, y2. Then if we multiply this, we'll get it 3x1 minus 2x2, and this one is minus 2x1 plus 4x2, and then y1, y2. We further multiply this, so you will get it 3y1 x1 minus 2y1 x2 minus 2y2 x1 plus 4y2 x2. So if you compare these two expression in the black ink, you'll see that both are same. So this proves that operator x comma y is equal operator y comma x. So this verify the symmetric property. The next property is the distributive property, in which we are going to show that x plus y multiply g is equal x y plus g. So for that, this definition is g transpose a x y. In this case, we consider g is like the same x and y, and from R2, and it denoted as G1, G2. So therefore, Z transpose will be G1, G2, and A is the matrix 3 minus 2 minus 2, 4, and X plus Y is X1 plus Y1, X2 plus Y2. Okay, then if we multiply this 3Z1 minus 2Z2, and then if we multiply togetherly, so this will be multiply x1 plus y1, and then this expression minus 2g1 plus 4x2, 4z2, and then x2 plus y2. We further open up and we collect the x1 and x2 terms. So we'll have 3z1 minus 2z2 x1 plus minus 2z1 plus 4z2 x2, and similarly we collect y1 and y2. And then we combine this x1, x2 part, and then this is equivalent to say z1, z2 matrix 3 minus 2 minus 2, 4, and then column x1, x2. Same way, this expression is written as z1, z2, the matrix A, and then y1, y2 in the column. So this is nothing but Z transpose AX. And this one is also Z transpose AY. So this means this is equal XZ plus YZ. So this is distributive we have here. The last property is with the scalar multiplication. So we take alpha is an scalar, so which is real number, and then alpha x y. By definition, this is equal y transpose A alpha x. So y transpose is y1, y2. A is the matrix as given, and alpha x will reduce to this matrix alpha x1, alpha x2. Then we process as before the multiplications, this two, and then with this you will get it here 3y1 minus 2y2 alpha x1 plus minus 2 y1 plus 4y2 alpha x2. So after multiplication, we'll see that alpha is common here. So we take out the alpha, and then you will get it here, same as y1, y2, and this matrix A, and then x1, x2. So this expression is alpha y transpose AX. So which is equal alpha inner product X, Y. So therefore, this verify all the properties of the inner definition of the inner product. Hence, this relation is an inner product.